Friends, I am Prashant V, Dhanshetti, Assistant Professor, Department of Civil Engineering from Walchand Institute of Technology, Solapur. Today I am here to explain you about how to calculate the design strength of compression member for steel structure. At the end of this session, students will be able to understand the classification of the buckling class for the compression member, numericals to calculate the design strength of compression member. So what is the compression member? So it is a structural member which is straight and subjected to two equal and opposite forces applied at its end. Different terms are used to designate the compression member depending upon its position in structure. Column, section or post. It is the vertical compression member supporting floors, and this generally carries heavy loads. Strut is a compression member which is used in roof truss or bracing. It is a small span and lightly loaded compression member. The strut may be continuous or discontinuous strut. So these are the steps to be followed to find out the design strength of compression member. Generally, the data given is rolled steel section, length of the column, then end condition of the column and grade of steel. The first step is to find out the properties of given rolled steel section from the steel table. Step number 2 is to classify the buckling class of the column, which is done as per IS 800 2007, table number 10, clause number 7.1.2.2. Third step is to find the minimum radius of gyration. So R minimum can be calculated by R minimum is equals to under root I minimum upon area. So this formula is used for built up section, whereas for single section R minimum is directly taken from the steel table. The K factor to calculate the effective length depending upon the given end condition of column is taken as per table number 11 of IS 800 2007, clause number 7.2.2. Then slenderness ratio is calculated using formula lambda is equals to KL upon R minimum. To calculate the design compressive stress FCD based on buckling class, slenderness ratio and grade of steel as per clause 7.1.2.1, then step number 7, the design strength is calculated using formula, that is PD is equals to AE into FCD. Now we will see the numerical. The question is calculate the design compressive load for a sanction 350 at rate 710.2 Newton per meter, which is 3.5 meter high. The column is restrained in direction and position at both ends. It is used as an uncased column in a single story building. Use steel of grade Fe410. So the weight per meter is also important. So here, according to this given data, the column section is ISHB 350 at rate 710.2 Newton per meter. The grade of steel is Fe410. Then height of column is 3.5 meter. End condition is restrained in direction and position at both ends. So going to solution, so we know the grade of steel Fe410, therefore Fy will be 250 Newton per mm square and Fu will be 410 Newton per mm square. The properties taken from the steel table are, first we have to identify which buckling class it will be there. So we know the Rz and Ry value. So Ry value is less than Rz value. The column will buckle about YY axis, and the design compressive strength will be governed by the effective slenderness ratio about YY axis. So for this a table is given, table number 10 of IS 800 2007, and the clause is also mentioned here. So accordingly we have to find this value, that is H upon BF, that is 350 upon 250, it is 1.4, which is greater than 1.2, and TF it is 11.6, which is less than 40 mm. So according to this condition 1 and 2, so here we can see this condition 1 and 2, it satisfies, and as Ry is less than Rz, the buckling will occur about YY axis. So this YY axis. So according to this, the buckling class of this section will be B. Now to calculate the effective length, that will be derived from the actual length and end conditions. The end conditions are given restrained in direction and position at both ends. So we have to search for this again in table number 11 of IS 800-2007. So here you can see this last one. This is the restraint in position. This is restraint in direction at one end. Again this is restraint in position and restraint in direction at the other end. Therefore the K value will become 0.65. So the L effective will be 0.65 into 3500, that is 2275 mm. Now to find out the slenderness ratio, the tendency of the member is to buckle is usually measured by its slenderness ratio. So here we have already seen that Ry is less than Rz, the column will buckle about YY axis. So we have to find out the slenderness ratio about YY axis. So again this is calculated as per clause 7.1.2.1 of IS 800-2007. So the formula here is, it is mentioned lambda. So lambda will be equals to, so this is Fy upon FCC under root. So this again putting the value of FCC, we will get this formula, that is lambda y is equals to under root Fy into bracket, that is KL upon Ry bracket square divided by pi square E. So we all know that the value of E for mild steel is 2 into 10 raised to 5. So Fy is 250, KL we have calculated, that is 0.65 is the K, and length of the column is 3500, Ry is 52.2. So putting all this value, we get lambda y is equals to 0.49. Now to calculate the imperfection factor, so accordingly the imperfection factor is given in table number 7 of IS 800-2007. So it depends upon the buckling class. So as our buckling class is B, imperfection factor for our case it is 0.34. Therefore alpha value is 0.34. Again we have to calculate phi y. So phi y formula is again given here in the IS code in the same clause 7.1.2.1. So we all know that the imperfection factor alpha is 0.34 and lambda y is 0.49. Putting this value, we get the phi y. So phi y value is 0.669. Now to find out the design compressive stress, again that formula is been mentioned here in the same clause 7.1.2.1. So FCD is equals to Fy upon gamma m0 divided by phi y plus into bracket phi y square minus lambda y square bracket close, that whole raised to 0.5, and this should be less than Fy upon gamma m0. So putting all the values, that is Fy is 250, gamma m0 is 1.1, then phi y is 0.669 and lambda y is 0.49. Putting all this value, we get FCD is equals to 202.11 Newton per mm square, and which is less than this Fy upon gamma m0 to 27.27, hence it is satisfying the condition. Now the design strength PD will be equals to area of that section into the design compressive stress FCD. So area of that section from the steel table we have taken 9221 into this FCD 202.11 into 10 raised to minus 3, it is to convert Newton into kilonewton. So the design strength will be 1863.65 kilonewton. One more method to find out the design strength of compression member, that is the second method, which is again an approximate method, and that is also given by IS code. The slenderness ratio is the ratio of effective length to the appropriate radius of gyration. So we have already taken the effective length, that is KL, and R minimum we know it is from steel table. So we can find out this slenderness ratio lambda is equals to KL upon R minimum. So this value comes out to be 43.58. And the buckling class we are already knowing it is about YY axis as RY is less than RZ. The buckling class is B. Now the design compressive strength FCD for buckling class B and the slenderness ratio 43.58 of the yield strength 250 Newton per mm square of steel. This is given in table number 9 of IS 800 2007. So here you can see the table from IS, it is there. So according to the clause 7.1.2.1, so here KL upon R value are mentioned here, lambda values, and here the yield stress has been mentioned, and the table is giving you the FCD values. So now our value of lambda is 43.58. So we have to interpolate this value between 40 and 50. So for 40 and 50, for 250, here you are having the values. So that is 194 for lambda 50 and 206 for lambda 40. So we have to interpolate between this to get the value of FCD for 43.58. So this is the interpolation method. So FCD will be equals to 194 plus bracket 206 minus 194 divided by 50 minus 40 and multiplied by 50 minus 43.58. So this is using the similar triangle properties also. So putting the values, the FCD value will be 201.704, and again the design strength will be equals to area of the member into FCD, design compressive stress. So 9221 into 201.704 into 10 raised to minus 3, it will give you 1859.91 kilonewton as the design compressive strength. Therefore, design strength by analytical method and using formula and the design strength using table are nearly equal. So these are the references which I have referred. Thank you very much for watching my video.